Now that we've learned about the properties of right triangles and we've learned about the law of sine and cosine, let's look at applications that possibly involve all three of these things. Let's look at an example. Lisa is 800 meters from the base of a mountain. From where she stands, she measures the angle of elevation to the peak of the mountain to be 38 degrees. She then walks to the nearest part of the base of the mountain. Lisa measures the new angle of elevation, this time getting 49 degrees. How far is Lisa from the peak of the mountain when she's standing at its base? Round your final answer to the nearest 100 meters. Okay, so let's take a look at this picture that's given to us. We have a triangle that represents the mountain, and we have Lisa positioned at the bottom left of that image. Lisa's standing there, and she looks out at a horizontal and then looks up for an angle of elevation of 38 degrees. She then walks 800 meters till she hits the base of the mountain, and she looks out at the horizontal again and up for an angle of elevation of 49 degrees. We are being asked to find, there's a question mark on this image, and so I'm going to call that X. We are being asked to find how far Lisa is from the peak of the mountain when she's standing at its base. All right, so I'm going to let X, I'm going to go ahead and define that variable. I'm going to let X equal the distance from Lisa to the peak of the mountain, and that is in meters. Important to put the units on there. All right, so that's in meters. Now let's take a look at what information has been given to us. We have been given an angle. We have been given a side. And we have been given another angle of 49 degrees. However, that 49 degrees is not part of the triangle that had the angle in the side. If we could determine this angle that is inside of that triangle, then we would have an angle side angle triangle, and we could use law of sines to solve for x, because x is the side across from the 38-degree angle. So what is that angle? Well, we were given 49 degrees, and 49 degrees in this unknown angle lie on a straight line. A straight line is 180 degrees, so if I subtract 49 degrees, I should be able to find out what that angle is. And when I do that, I get 131 degrees. So that's nice. I have angle, side, angle. So using law of sines, I can say that x over the angle across from it, the sine of 38 degrees, is equal to, now I need an anchor, don't I? I was given 800 meters. Do I know the angle across from that? That would be the angle that's up at the very top. That is not being given to us, but I do have the other two angles, don't I? So this angle at the top would be whatever 180 degrees minus the 38 degrees that was given, minus the 131 degrees that we found, and I believe that that's 11 degrees. It's very small, but it is the angle that's across from that 800 meters. So that is my anchor, and I can say that this is equal to 800 over the sine of that 11-degree angle. Okay, so what does x equal? I'm going to multiply both sides by the sine of 38 degrees. That gets me 800 times the sine of 38 degrees all over the sine of 11 degrees. That's what I'm going to put into my calculator. And when I put that into my calculator, I got approximately, I got 2581.268. I'll just give you all these digits, 138. Okay, so that's what x is. Now, this one asked me to round to the nearest 100 meters. That's not hundredth, that's 100. 100 is in the, let's see, this is the 1,000, this is the 100, this is the 10, this is the 1. So if I round to the nearest 100, this 8 tells me to round up, doesn't it? So I'm going to say that Lisa is approximately 2,600 meters from the peak of the mountain. From the peak of the mountain. And I think that does it. So I use law of sines. Let's try another one. A billiard ball starts 86 centimeters from the corner pocket as shown. All right, let's just make sure we see that. So 86, here's the ball, and the corner pocket is right down here, and they are 86 centimeters apart. The ball rolls 120 centimeters in one direction. It hits the rail. Okay, so we hit the ball, goes 120 centimeters, it hits the rail, bounces off, goes 100 centimeters, and straight into the pocket. How convenient is that for us? It just formed a triangle. What is the angle between those two paths before and after the ball hits the rail? Round your final answer to the nearest degree. All right, so this question mark I'm going to call x, and I'm going to define x to be equal to the angle between the paths of the ball. The path of the ball, I'll say. And that is in degrees. Not in radians, it's in degrees. So that is my unit in this case. Now, what has been given to me? What has been given to me, we started with the 86, then the 120, and then the 100. So we have a side, side, side triangle, and that is the law of cosines. It's really helpful, I think, to identify what type of triangle that you have so that you know exactly what properties you should use. Okay, so I want to find angle x, and that's in degrees, and so I need to connect that with this side of 86. I'm going to say that 86 to the second power is equal to 120 to the second power plus 100 to the second power minus 2 times 120 times 100 times the cosine of whatever x happens to be, and that's in degrees. You can understand maybe when I said earlier committing the law of cosines to memory, you write this out enough times and it starts to feel like you just know it. You're not memorizing it, you just know it. At least that's my hope. All right, so now I'm going to start trying to solve for the cosine of x. And so what I have to do then is isolate that. So I'm going to take 86 squared, I'm going to subtract 120 squared, I'm going to subtract 100 squared, and that's going to equal negative 2 times 120 times 100 times the cosine of x. I will divide both sides by that negative 2 times 120 times 100, right? Those will all cancel out on the right, but then I have to do it on the left. And you'll notice that, yeah, I could probably multiply those out, and I could write just one number, but I can also just put this whole numerator into my calculator and divide it by this whole denominator to end up getting that the cosine of x is equal to, when I put that all in, I got 0.7085. Now that's not the answer for the angle, that's the cosine of the angle. So now I need to take the inverse of each side, and I'm writing it out. So cosine inverse 0.7085. Don't get lazy in how you write this. You want to make sure that your notation is good. And the inverse undoes the cosine, and I'm left with x being approximately 44.89, and that's in degrees. So the question was, what is the angle between the paths? And round your final answer to the nearest degree. So I'm going to say the angle between the paths, or the path of the ball to the nearest whole degree, is going to be 45 degrees. Let's try one more example. Sherman needs to determine the height of a tree before cutting it down to make sure that it won't fall on top of a nearby fence. The angle of elevation from one position on a flat path to the tree is 40 degrees. And then from a second position, 20 feet farther down the path, is 30 degrees. What is the height of the tree? Round your final answer to the nearest foot. All right, so we have a tree. Should I make that tree green? Here's my tree. And make that tree. I'm going to assume that tree is perpendicular to the ground. And let's see, what else do I know? Sherman is on the ground on a flat path. And angle of elevation is to the top of the tree is 40 degrees. So this angle right here is 40 degrees. And then from a second position, 20 feet farther, so this piece here and this piece here is 20 feet. And now the angle of elevation is 30 degrees. It's a little smaller, which is making sense with my picture. What is the height of the tree? I'm going to call the height of the tree h. And don't forget, I said we're going to assume that that tree formed a right angle. So I'm going to say let h equal the height of the tree, in feet. Okay, now because the height of the tree is part of a right triangle, I might be able to use my SOHCAHTOA rules. I know the 40 degrees that's across from h. So I could say, let's see here, across or opposite, I could say that the sine of 40 degrees is equal to the side opposite over the hypotenuse. Well, the hypotenuse I'm going to call x, and I don't know x. So that's not getting me too far. However, I do have this other triangle that's inside. Let me just shade it. It's this little sliver of a triangle. And the reason why I'm thinking about using that is because I have this 20 feet on the end. I know 20 feet, I know 30 degrees. I think I could find this angle that's right here on the inside, because that angle, along with the 40 degrees, forms a straight line, which is half of a circle. So I could say that that angle is whatever 180 degrees minus 40 degrees is. That's 140 degrees. That tells me that the angle up at the top is whatever is left over to get me to 180 degrees. So I've got 180 degrees minus the 140 degrees I just found, minus the 30 degrees, and that's going to get me a 10-degree little angle on the inside. And that I like, because that 10-degree angle, along with my 20 feet, and the 10-degree angle, I've just got my anchor, don't I? So what I want to do is solve for x and then use that x value to then solve for h. So I'm going to say that x over the sine of 30 degrees is equal to the 20 feet over the sine of 10 degrees. And I'm going to multiply each side by the sine of 30 degrees to get that x is equal to 20 times the sine of 30 degrees all over the sine of 10 degrees. And when I put that into my calculator, I got that x is equal to 57.58770483. Now, that is not my final answer. That is simply the thing that I'm going to use to substitute into my SOHCAHTOA. So I'm going to say that this is equal to h, the sine of 40 degrees is equal to h over approximately 57.6. Now, of course, I'm not going to use the 57.6 in my calculation. I'm going to use the full number. Now, I will multiply each side by that 57.6 so that I can say that h is equal to whatever 57.6 times the sine of 40 degrees is. And when I put that into my calculator, I got that h is equal to approximately 37.02 feet. This one asked me to round to the nearest foot, so I'm going to say that the height of the tree is 37 feet. So this is an example of a problem where we really have to take all the things that we know, the right triangle rules, law of sine, law of cosine, and determine maybe we have to use one of them, maybe we have to use two of them, but we have options, don't we? And that's really the way you should think of these, not just in isolation, but how do I use all of these properties that I've been learning in order to solve problems?